Hello. Uh, so uh, Today I'm going to be talking about information extraction pipeline. This is how to get from unstructured data to knowledge graph. And as we'll see, basically the unstructured data is the text. So before I start, a little bit about myself. So my name is Tomaž Bratanič. I'm a graph data scientist, and if you've been around Neo4j, you might have seen some of my blog posts, and you might have also seen I've also did a presentation last year around a similar topic, and this year I'm gonna expand a little bit on that. As mentioned, information extraction pipeline. So for the input, what we'll do, or what I did, is the input to the pipeline is text. So that could be like in various forms, like you could have like text stored in your PDFs, or you can scrape web pages. For example, if you want to scrape news sites, you could have like text files, or like if you're a journalist, you could also investigate emails and input that into the pipeline, or you could also, like if you're like in a business environment, you could also input messages from the messaging platform and input that into the information extraction pipeline. And as a result, ideally what you will get is a knowledge graph. And I'm certain you've heard knowledge graph today a lot, but just to give you like a quick idea. So basically, a knowledge graph has nodes that represent real-world entities, or real-world entities or concepts. And so nodes can be of many types. For example, there's the person type. It could be the nodes with course type, or like location types. And we have relationships between those nodes. So, like located in, like lives in, and works with. So, like in my humble opinion, so when you've got a single relationship type, then you're not dealing yet with a knowledge graph. But once you have more than a single relationship type, then you are dealing with a knowledge graph. So that's basically like the high level overview. So input is text, output is knowledge graph, and how to get there is I've implemented information extraction pipeline a few months ago as like a hobby project, and my information extraction pipeline consists of 4 steps. So the first 3 steps are basically NLP techniques, and then we store the results of the NLP techniques into a graph database. As you might have observed, in this talk, I won't be talking so much about how to analyze your knowledge graph, but more on how to construct a knowledge graph with the help of NLP techniques. I feel like this is really important because nowadays, like there's like a wealth of information generated every day. You've got like if you're in a business environment, you've got like emails or PDFs or a whole bunch of text, or like you've got also a whole bunch of text generated on internet, because you've got like internet forums, you've got news web pages, and I feel like this information extraction pipeline will be more and more relevant in the future. So, as mentioned, the first step is the coreference solution. Coreference solution is like excuse me, an NLP, so a natural language technique, which finds all expressions that refer to the same entity in a text. So, like in simple words, is what it does. It finds all the pronouns and then replaces them with the referenced entities. And those could be like personal, locational, or possessive pronouns. So I've got a simple example. So if we would input Elon Musk was born in South Africa, there he briefly attended classes at the University of Pretoria. So you can see that the first sentence doesn't have any pronouns, but the second sentence has two pronouns, one locational and one personal pronoun. So the ideal result of the Coreference solution model would be an output that changes there with in South Africa and replaces he with Elon Musk. So we would end up with in South Africa, Elon Musk briefly attended classes at the University of Pretoria. So this might seem like a really basic result, not so complicated. But believe me that like real-world examples of coreference solution could get quite complicated. And it's also a very important step, although it might seem very basic in the information extraction pipeline. So once we've done that, once we've dealt with coreference solution, we move on to the named entity recognition. So named entity recognition is a task of basically recognizing all the mentioned entities in the text, and those entities could be of various types. For example, we could have a person, a location. GP here actually means, I think, a geopolitical entity, and we also have like organizational entities. And basically, it will find the entities that the model was trained on, and obviously, the training data really depends on the domain or like the intended application that you are using it for. And so there are like a couple of limitations to named entity recognition. I will just point out the most maybe obvious is that here I've added an example where Elon Musk basically is in three different sentences, and once he's referenced or mentioned with his full name. The second time he's mentioned as Mr. Musk, and then in the third sentence he's mentioned as Elon. And in our knowledge graph, in our output knowledge graph, ideally we want a single real-world entity to be represented with a single node. So we really don't want to have like three different nodes representing the same entity as we would have here if we would just use the results like we have here. And as mentioned before, the named entity recognition model depends on the domain or the intended application, and most open source models are trained on like news or like forum types of text. But like, for example, if you wanted to analyze biomedical text and like extract biomedical concepts like genes or drugs or diseases, then obviously you would need to use a different NLP model that was trained to extract biomedical concepts. And as most of you know, or as anyone who's dealt with machine learning or NLP no model is 100% accurate. And even when I was preparing this example, in the third sentence, if I just switched the word names and started the sentence with Elon, so it was like Elon favorite lessons for engineering, then Elon was not recognized as a person. So the spacey model that I used here didn't recognize Elon as a person. So you kind of have to take that all into account. So how could we solve the entity disambiguation so that a single real world entity would be represented with a single node in a knowledge graph? And that's called entity linking. So we go from named entity recognition to named entity linking. And entity linking basically means that we upgrade the named entity recognition to first recognize all the entities and then map those entities to a target knowledge base. And very frequently that target knowledge base is Wikipedia. So in essence, we recognize the named entity linking model recognizes entities in the text and then links them to Wikipedia ID. So here you can see that I've added a Wikipedia ID for all three entities. So ideally, the result would be that even though we have three different records of text for Elon Musk, they would all link to the same entity on Wikipedia, and we could use that Wikipedia ID as identifier for nodes in our knowledge graph, and we would end up with a single node in our knowledge graph. And this process is so common that linking entities to Wikipedia is actually called wikification. And on the plus side is we don't have to worry about which text record is correct, because here we have three different text records that refer to the same entity, but we could just use the Wikipedia ID and then get the text name, or basically the entity name from Wikipedia. So we don't really have to worry which text record is correct. And on the plus side is that once we've got Wikipedia IDs for our entities, we can also use Wikipedia to enrich our knowledge graph. So you could combine the information that you got from the information extraction pipeline with online information that is available on Wikipedia and use that to create a more full knowledge graph. And some of you might say that Wikipedia might not be the most accurate source, and I might agree, but I will also say that Google uses Wikipedia extensively, so if it's good enough for Google, it's also good enough for you and me. And here we could also say, okay, so this is good enough. We'll stop with the NLP techniques and just create a graph out of this. So when you only have entities in the graph and okay, so basically co-occurrence networks for graphs are basically when you infer relationships between a pair of entities based on their presence within a specified unit of text. So, for example, we could say that if two entities co-occur or are present in the same sentence, then we say that they are somehow related. We don't really know how, but we just know that they are somehow related because they appeared in the same sentence. And here you can also see that the coreference solution was quite important, because if we split the specified unit of text into a sentence, if we didn't use the coreference solution, here in the second sentence we would only have a single entity and two pronouns. So our information extraction would not be full, or we would have like a loss in the extraction pipeline that we can avoid by doing the coreference solution. So basically this was my last year's topic, but because the co-occurrences networks were my last year topic, but because this is a new year, we've moved forward. So what if we want to extract semantic relationships from text, and we don't just want to have like a generic relationship between them where they all kind of co-occur, so they are somehow related, but we don't really know how. And we want to give basically types, or like define semantic types to relationships between a pair of entities. So those categories of relationships are usually categorized. So for the readability of your knowledge graph, you can have some categories of relationships that you want to infer between a pair of entities. And you could do that there are two different approaches. So one is the rule-based relationship extraction, where you're using grammatical dependencies of the text to extract relationships. Or again, you can train an NLP model to extract relationships between pair of entities. So first, we'll take a look at rule-based relationship extraction. So I've used spaCy to visualize the grammatical dependencies of the sentence Elon Musk was born in South Africa. And for those of you that are familiar with RDF graphs, this will feel kind of intuitive, because RDF graphs use data structure trippers, where you basically have a subject, a verb, or predicate, and the object. So basically subject and object are two nodes, and then in the middle there's the verb or predicate, which is the relationship between those two entities. And that can be translated to grammatical dependencies. As you can see, we've got the verb, which is in the middle. We've got the subject of that is Elon Musk, and we've got the object, which is South Africa. So we've got Elon Musk is subject, born is predicate, and object is South Africa. And so we can infer that actually Elon Musk was born in South Africa, instead of just having a co-occurrence genetic relationship between them. So there are obviously some pros and cons to this, and like an intuitive con to using this approach is that there could be like many types of relationships, so you're not really doing any semantic categorization of your relationships, because you're just taking the verb. So you could have a verb which has the time component, so it could be present, future, past tense, which might or might not be a good idea to persist to the knowledge graph. And there could be like some like synonyms of verbs that you could have like different relationship types that have like a similar or identical semantic value. So like my suggestion would be to you that if you use the rule-based relation extraction, then you also do a little bit of post-processing of the verb and try to fit it into like some semantic categories so that you don't end up with so many relationship types. So, for example, you could lemmatize the word, then you can kind of use synonyms to group some verbs into the same category, relationship category, and so on. And then the other approach to relation extraction is using again an NLP model. So again, you have to train your NLP model to infer relations between pairs of entities. And again, the types of relationships that are inferred depend on the training data that is used to train the model. So, for example, if you're you're using news, you want to have a different model than if you are analyzing like a biomedical article. And as far as I know, there aren't many data sets available, but there are some. So, for example, TechRed is the data set made available by Stanford. And then there's also the Wiki80 data set, which we'll take a look a little bit more in detail. So the Wiki80 training dataset contains 80 different relationship types. The relationship types conform to Wikipedia or Wikidata standard. So the same semantic categories of relationship used in Wikipedia are also used in the training data. So, and I believe that people who made Wikipedia kind of know what they're doing. So I kind of would trust their categorizing of relationships. And for me, it's really interesting to see that if you use Wikipedia as the target database for entity linking, so basically you're linking named entities to Wikipedia, and then you also use a Wiki80 training dataset, so you try to infer the relationships that conform to the Wikipedia ontology between pairs of entities. What you're actually doing is constructing your own mini Wikipedia-like knowledge graph, which to me sounds quite awesome. So basically, you're inputting some text, and at the output is like a Wikipedia-like knowledge graph. So I feel like that's really awesome. So now we're gonna look at like a real-world example of using information extraction pipeline and use it like for direct repurposing. So what basically you need a knowledge graph with medical concepts. So you can have many types of nodes. So this could be like genes, drugs, diseases, or other types of nodes. And there could be also many types of relationships between those medical concepts like treats, causes, predisposes, and other relationship types between medical concepts. And then what you would do is you would basically do link prediction for the treats relationship, and this would basically predict you would basically try to predict new uses for the drug. So that's basically the direct repurposing. So how you would approach it? Basically, you would use text input into the information extraction pipeline, and there are like many medical journals that you can use. The most famous, at least as far as I know, is the PubMed. So you've got like, I don't know, couple of thousand. I don't really know, but there's like lots of medical papers that you can use as an input that into your information extraction pipeline, and then do named entity linking. So this time you wouldn't use Wikipedia as the target database, but there are like many online medical target databases that you could use. Like you could use Interest or Ensemble database to map genes to their corresponding IDs in the target database. There's also CHEBI or CHEBI, I don't know how it's pronounced, for like chemical substances. So basically you do the named entity linking, and in the biomedical world, this is a much harder problem for the entity disambiguation than it was in the example that I showed with the Elon Musk example, but that's like a story for another time. So once you have your biomedical concepts extracted, now what you need to do is extract relationships between those entities, and this is a big problem, and not almost no existing training datasets are available. But it is what it is. There's available a semantic Medline database where a group of scientists and doctors came up with a rule-based relation extraction, and their data is available on their website, and you can use that. You could also use that to train your custom NLP model, and then try to extract relations with your own database model, NLP model. And now that you have biomedical concepts as entities and relationships between them, you create a knowledge graph and try to predict new use cases for existing drugs. So here I've made like a simple, just a simple example where we've got drugs and diseases, let's say diseases. But obviously the real world example is much more complicated, because you could have also like genes. So like headache could be associated with the same genes as migraine, and then there are also relationship between genes, and it could get complicated quite fast. But like just to give you like a simple idea, so for drug repurposing, what you then do is basically do link prediction, or as it's called, knowledge graph completion. So when you're trying to predict new links, but also their type, it's called knowledge graph completion, because it's quite different if this new relationship, predicted relationship, is traits, or if this new potential relationship is causes. So yeah, this is like a simple real-world example of using information extraction pipeline to construct a knowledge graph, and then use that knowledge graph for the cool applications using knowledge graph embeddings, maybe graph neural networks and stuff like that. So that's basically it for my talk. I've got my implementation, as I showed in the beginning, for the Elon Musk. It's on GitHub. So if you clone this repository, you can use it and play around with it. And there's also a blog post where I've written about that.